Hi everyone, this is Miss Lorette here. This is going to be a video covering section 7.6, which is all about exponential functions. You'll want a calculator for today's lesson just to make some of the calculations a little bit easier to do. So let's go ahead and dive right in and look at an example to open the lesson. So it says that your soccer team wants to practice a drill for a certain amount of time each day. Which plan will give your team more total practice time over 4 days? And then how about over 8 days? Explain your reasoning. So for plan one, you're going to start with 5 minutes today and then 1 minute more each day than the previous day. For plan two, you're going to practice for 1 minute today and then twice as much time each day as the previous day. I encourage you to pause the video, maybe even make a table of values for each plan, and see what type of conclusion you end up with. I will pause my video here, and then when you unpause, you should see some work on the screen to explain a solution. Okay, hopefully you've given that some thought. So here's all of my supporting work. Again, I just made a table of values where we've got our days and our time. So for plan one, we're starting with 5 minutes and then just adding one additional minute for each and every day. To get your total practice time, you're going to add all of this time up. So for 4 days, you're going to practice for a total of 26 minutes. Over 8 days, and you add up all of this, you'll get a total of 68. For plan two, same idea, but when you want to calculate your practice time, rather than adding the same amount over and over, you're doing twice as much as the previous day. So you're multiplying by two. So 1 times 2 gave me 2, 2 times 2 gave me 4, 4 times 2 gave me 8, so on and so forth. My total when I add up the time for 4 days was 15 minutes, but then over 8 days, it's 255. So what ends up happening is that for plan one exceeds plan two by a little bit for the first 4 days, but then plan two far exceeds plan one as much as time goes on. It just keeps growing bigger and bigger. Plan two is actually an example of the type of function that we're going to be talking about in this lesson, and that is an exponential function. And I know there's a lot of info on this slide, so again, pause the video if you need to copy everything down first, and then I will go through and explain what all of this means. So these are, a few graphs of what an exponential function looks like. And the first thing you probably noticed is that it's not a straight line. It's got some curve to it. All of the functions that we have really graphed in this class so far have been straight lines. So the first thing you probably notice is that this one is not straight. These are examples of exponential functions, and the equation follows this format. You've got some sort of coefficient, which we call the a value. We refer to this as the initial amount. And we have all this criteria about the values in the equation. We don't want the a value to be 0. Let's think about why that is. If I replaced the a with a 0 and then I multiplied with this power, what do you think is going to happen to the right side of my equation? Everything's going to become 0. So you're left with the equation y equals 0. That's not exponential. That's linear. That's a horizontal line. So we can't have the a value equal to 0 because we want to make sure that this function is exponential. We also have two criteria for the b value, which we call our growth factor. And this is just the base of our power. The base has to be positive, and it also can't equal 1. Okay, so let's think about why it can't equal 1. If my base is a 1 and I raise 1 to any exponent, what's going to happen? Well, my output, regardless of what that exponent is going to equal 1. So you're just going to get 1, 1, 1. Your output's going to be the same. So again, that's not then going to be exponential when we graph it. It's going to be a straight line. We don't want that. We want it to be exponential. So we have to stipulate that the b cannot be equal to 1. And notice where our x is. Our x in this particular function is an exponent. Okay, so all of the functions that we really worked with up to this point in this class, the x was not an exponent. It was kind of functioning kind of like a coefficient. We were multiplying or adding to it. So in this particular function, it's an exponent. So let's just take a look at some pretty easy examples where all we're going to do is identify those two things within the equation. What's the initial amount A? So what's our coefficient? And what's our growth factor? What's our base for that power? And as I do these, I encourage you to pause the video and give them a try on your own first. The first one's really easy because the numbers are the same, but it's important to understand that our A value, our initial amount, is the 1/4 that's actually not in the parentheses. It's that coefficient. Our initial amount, if we looked at the graph, that's what our output for our function is going to be when the x is 0. Okay, so if you think of x as like the amount of time, like in that second plan 2, at time 0, our initial amount was 1. Okay, so when your x is 0, you're just going to be left with A. Our growth factor is also 1/4, but specifically in this function, it is the 1/4 in the parentheses. It's the base of your power. You can almost think of B standing for base. Let's take a look at number 2. My initial amount A is going to be my coefficient of 3, and my growth factor is 2. Okay, your growth factor is just your base. And again, I encourage you to try 3 and 4. For 3, you should have gotten that the initial amount is 2 and the growth factor is 1/3. For number 4, your initial amount is 1/3 and your growth factor is 6. Okay, so it's important to understand the difference between those two things. Let's take a look at another example. And this is where you're really going to want to start, having your calculator handy as we start doing some math with these functions. Suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week. So think about what that means, doubling or twice, kind of like in that plan 2 example. You're multiplying by 2 every single time. That's actually our growth factor. It's doubling. Okay, so that's where the 2 comes from in this function. This is the function that gives the population after X weeks. So X represents number of weeks. The 2 is our growth factor. It's that doubling factor. The 30 is the initial amount. That's our A value. We want to know how many beetles will there be after 56 days. Now, be careful with the format that they're giving us the time in. 56 days is not number of weeks. We're not going to substitute 56 for our x value. We need to first figure out how many weeks is in 56 days because we want to input some number of weeks. All we're going to do is evaluate this function for specific input. We did a little bit of this in chapter 4, so I encourage you to go back, look at your notes for that, or even watch the video that goes with that. All we're doing is replacing the x with a number and simplifying or evaluating. So I first need to figure out how many weeks is in 56 days. Well, I know that there's 7 days in a week, so if I divide this by the amount of days in a week, that should give me the number of weeks. If I divide this, that's going to tell me that I have 8 weeks in 56 days. So this is actually what we're replacing the x with. The x is going to be 8. So instead of evaluating f of x, and again, f of x is just another way to say y, it's going to be f of 8. And I'm just going to replace anything that has an x. Oops, not x. It's going to be replaced with an 8. And then I just evaluate this. I'm going to do the power first. I'm just following order of operations. And this is probably where you're going to want to use a calculator to make quick work of it. 2 to the power 8 gives me 256. And then I multiply last. If I multiply that with 30, I get 7680. So 7,680 beetles. That's how many, according to this problem, will be there after 8 weeks. So let's take a look at one that you can try. I'm going to pause the video here. So when you unpause, you should see a solution. So pause the video yourself on your end, give it a try, and then let's compare. Okay, so here's what I ended up getting. So the tricky part about this problem, again, is the number that they're giving you is not actually what you're going to input for the value of x. X in this function represents the number of half years. So if you think about 1 year, there's 2 half years, right? Half a year is 6 months. So there's the first half of the year and the second half of the year. So there's 2 half year periods in 1 year. So if you look at 3 years, you're going to do, 2 half years each of those years. So you're going to multiply each year by 2. That's going to give you 6 total half year periods. This is actually what you're inputting for the value of x. Once you know what to replace the x with, it becomes an order of operations problem using your calculator. You're going to evaluate the power first to get 729, and then multiply that answer with 20 to get 14,580 rabbits. So if you understand how to then evaluate this function, once you know what to substitute, then graphing actually should not be too difficult because you're doing basically the same thing, but you're just inputting different numbers. So let's take a look at a few graphing examples, and hopefully I can wrap this up before my class comes in. It says sketch the graph of each function, use a table of values, and it's best to use inputs that are negative, positive, and also 0, just to get a clear image of the graph. So I usually choose, a negative value, maybe -2, 0, and maybe +2. You don't have to do a ton. So let's go ahead and do an example. So I've got my x values, and I've got my y values. And let's do -2, 0, and +2. Some teachers may require that you do, 5 points. I think I may even have a few assignments for my students where I use 5 points, but for the sake of time, I'm just going to do 3. And for some of these functions, you may have to actually estimate where the points sit on the graph. You might not always get nice numbers, so just kind of keep that in mind. For an x value of -2, we're just going to replace that exponent, with a -2. And we learned that a negative exponent just says to take that power and move it to its reciprocal location. So if I simplify this, that's going to give me 3/4. And again, I can actually maybe make this a decimal if I need to get a clearer image of where it's going to sit on my graph. This one works out nicely. This would be 0.75, so it's a little bit less than 1. So if I plot that, I'm going to go left 2 times and then almost up to where that 1 would be. If I replace my x with a 0, anything to the power 0, we learned, is just a coefficient of 1. So 3 times 1, that's going to give me 3. And notice that that output, when my input is 0, it's just that a value. That's going to be the case for every function. When you replace that x with a 0, you're just going to be left with that initial amount. That's why we call it the initial amount. At time 0, or an input of 0, this will be your output. For an input of 2, I'm just going to replace my exponent with 2. I'm going to square the 2 first to get 4, and then multiply to get a final answer of 12. So if I plot these remaining 2 points, 0, 3 would be right here on the y-axis, and then 2, 12 would be up here. So again, the more points you plot, the clearer image you're going to get. So to the best of my ability, I'm going to curve these points together. So I even encourage you to do more points than just three. Maybe do two negatives, two positives, and zero. And the more points you have, the easier it's going to see how to connect them. Let's take a look at another example here. So we've got x, y, and I think again, for the sake of time, I'm just going to do -2, 0, and 2. And remember, for an input of 0, you're just going to be left with that initial amount a. So I know that this output is going to give me 5 right away. So I'm just going to do my others. For an input of -2, remember that a negative exponent tells me to just rewrite this value as its reciprocal. So it's going to be 2 over 1 or just 2 to the positive 2. And now I evaluate. I do the power first, which gives me 4, and multiply last, which gives me 20. So at -2, I'm all the way up here at 20. At 0, I'm up here at 5. And then at 2, let's see where we are at 2. 1/2 to the power 2. I'm going to square that 1/2 to give me 1/4, and then multiply with 5 to give me 5/4. 5 divided by 4 gives me 1.25, and I'm going to estimate where that point sits. It's a little bit past the 1. So again, the more points you would plot here, the easier it's going to see, the easier you'll see where, that function actually sits on your graph. So I encourage you to do maybe more than 3. Oops. Here's one for you to try. I'll pause the video here, give it a go, and then when you unpause, you should see a solution. Okay, so I ended up just using the same input values as before. I just used -2, 0, and 2. Again, the more values you use, the more clear that your graph is going to be. I was able to do the 0 without having to show any work because, again, at an input of 0, you're just going to be left with that initial amount, so your a value. And then here's all of my supporting work for how I got 18 and then 0.222. So notice for this input, I ended up getting a non-terminating decimal. Again, decimals, rounding your decimals here will probably be the easiest way to graph these because you're going to have to estimate where some of the points sit. So for this one, when I go to the right 2 times, to the best of my ability, I didn't even go up half of a grid line. 0.2 is less than a half. So I just kind of put it right there. And then to the best of my ability, using this tablet, I tried to connect them. Let's see if we've got another one. We do. Okay, so I'm going to pause the video again, give this one a try. Okay, now hopefully you've given this one a go. And here is what my graph kind of looked like. Again, just for the sake of time and simplicity, I just used 3 inputs this time, the same ones as before. I was able to calculate what my output would be for an input of 0 right away, because that should always just give you your initial amount. For my negative exponent, remember that a negative exponent moves that base to its reciprocal location. Evaluate your power, make it a decimal for ease of graphing. You get a nice terminating one here. So that point is going to be right here, somewhere around there at -2, 1.25. Your y value, you're not even quite to that halfway point on that first grid line, so I just kind of had to estimate. 0, 5 sits right here on the y-axis, and then 220 is all the way up here. Okay, so again, the more points you plot, the better you're going to see how to connect those points. And I believe that was the last one in my slides. So hopefully you found this video helpful. As always, if you're confused on anything, reach out to your math teacher, and I will see you guys next time. Take care.